Welcome back, students. Dear students, in this session, I would like to share the topic third law of thermodynamics. Let us see the third law of thermodynamics. In 1906, Nernst proposed a general principle supported by a series of experimental evidences on the problem of atomic heat at low temperature. Let us see the statement of third law of thermodynamics. It states that the heat capacities of all solids tend to zero as the absolute zero of temperature is approached, and that the internal energies and entropies of all substances become equal there, approaching their common value asymptotically tending to zero. Totally, the third law of dynamics may therefore be regarded as the principle of unattainability of the absolute zero of temperature. This law is also known as the Nernst heat theorem. Here the simplest statement of Nernst follows neither from the first law nor from the second law, and is thus of the nature of the new law, usually called as third law of thermodynamics. Let us see in detail regarding this law. This theorem is useful in explaining the nature of bodies in the neighborhood of absolute zero temperature. Its importance lies in the fact that it permits the calculations of absolute values of entropy, Helmholtz and Gibbs, free energies, etc. In terms of entropy, the theorem may also be stated as at absolute zero temperature, the entropy tends to zero and the molecules of a substance or a system are in perfect order, that means well arranged. At a temperature of 0 Kelvin, the following phenomena can be observed in a closed system. First one is the system does not contain any heat. Here at absolute zero of Kelvin, we can observe in a closed system like the system does not contain any heat and all the atoms and molecules in the system are at their lowest energy points. Therefore, a system at absolute zero has only one accessible microstate, that is its ground state. As per the third law of thermodynamics, the entropy of such a system is exactly zero. Here in this case, at absolute zero, you can see the diagram here, entropy in a molecules of a system. Here at absolute zero, the entropy is zero. when the temperature increases, then it becomes, see in the diagram B, when the temperature is greater than 0, the entropy also increases. Here entropy is greater than 0 here. In all heat engines, there is always loss of heat in the form of conduction, radiation and friction. Therefore, in actual heat engines, the ratio Q1 by T1, that means energy gain, is not equal to the energy loss, that is Q2 by T2. Therefore, heat gain minus heat loss is not zero, but it is positive quantity. When cycle after cycle is repeated, the entropy of the system increases and attains a maximum value. When the system has attained the maximum value, a stage of stagnancy is reached and no work can be done by the engine at this stage. Let us see in the universe, the entropy is increasing and ultimately the universe will also reach a maximum value of entropy when no work will be possible. With the increase in entropy, the disorder of the molecules of a substance increases. The entropy is also measure of the disorder of the system. With the decrease in entropy, the disorder decreases. At absolute zero, the entropy tends to zero and the molecules of a substance or a system are in perfect order. That means they are well arranged. This is known as the third law of thermodynamics. For example, the molecules are more free to move in the gaseous state than in the liquid state. The entropy in the gaseous state is more than in the liquid state. The entropy in the liquid state is more than in the solid state. Thus, when a substance is converted from solid to a liquid and then from the liquid to the gaseous state, the entropy increases and vice versa. When ice is converted into water and then into steam, the entropy and disorder of the molecules increases. When steam is converted into water and then into ice, the entropy and disorder of the molecules decrease. Hence, entropy is a measure of the disorder of the molecules of the system. By an ideal procedure, it is impossible to bring any system to absolute zero temperature, performing a finite number of operations. This is called the principle of unattainability of the absolute zero. Hence, the third law of thermodynamics may therefore be regarded as the principle of attainability of absolute zero of temperature. Let us see what is absolute zero. Previously, we learned about the third law of thermodynamics, which states that the entropy of a perfect crystal at absolute zero is exactly equal to zero. According to the third law, the reason that when the absolute temperature is equal to zero cannot be reached is explained like this. Suppose the temperature of a substance can be reduced in an isentropic process by changing the parameter x from x2 to x1. As an example, one can think of a multi-stage adiabatic magnetization demagnetization cycle setup where a magnetic field is switched on and off in a controlled way. For this, you can see the diagram. The parameter x in this case would be the magnetization of the gas. This one. Assuming an entropy difference at absolute zero, here T equals 0, could be reached in a finite number of steps. However, going back to the third law, at T equals 0, there is no entropy difference, and therefore an infinite number of steps would be needed for this process. See here, temperature entropy diagram here. Horizontal lines represents isentropic process, while vertical lines represents isothermal processes. Here left side, absolute zero can be reached in a finite number of steps if entropy when T equals 0, then x1, which is not equal to entropy of T equals 0 when it reaches x2. In the right side diagram, an infinite number of steps is needed since entropy, that means S of 0 x1 is equal to S of 0 x2. Let us see the 0 point energy. According to kinetic theory, the energy of a system at absolute zero should be 0. It means the molecules of the system do not possess any motion. But according to the modern concept, even at absolute zero, the molecules are not completely deprived of their motion and hence possesses energy. The energy of the molecule at absolute zero temperature is called 0 point energy. The energy of molecules at absolute zero temperature is called 0 point energy. Now adiabatic demagnetization cooling. Here this same concept will be comes under the real gases, in case of real gases also. Let us see in brief the adiabatic demagnetization cooling. In simple terms, the cooling scheme mentioned above occurs by repeating the following steps. First one is a strong magnetic field is applied to adiabatically align magnetic moments of the particles in the gas. Second one is the magnetic field is reduced adiabatically and thermal energy of the gas causes ordered magnetic moments to become random again. In the second step, the thermal energy in the gas is used to cause disorder of magnetic moments. Therefore, the temperature of the gas is reduced, hence cooling works. This scheme is called adiabatic demagnetizing cooling. That's all. Thank you.